Hey, this is Ken Rosever, and we're going to look at some problems dealing with solving radical equations and inequalities from the old Unit D review for my college algebra class. Okay, so I'm going to go through this and I'll try to bring out some important facts as we go. But basically, you have a square root here, you have a linear equation there, you're trying to solve it. There's a number of methods, but if you're doing this by hand, the prescribed method is to get rid of the square root by squaring both sides. This is a 1/2 power, a square root is, so how do you undo a 1/2 power? You square it away. So I'm going to square both sides here. And this side squared is that, this side squared is this. And then squaring this, there's a shortcut for squaring binomials. It's the square of this, double the product of these two, plus the square of that, and then we have this. So we started with something that was radical and linear, and now we have a quadratic. So move this all to one side, subtract 2x, you get negative 8x, add 3, you get 12, and factor or use quadratic formula. When you factor, you find 2 factors of 12 that add to negative 8. There they are. And you set each factor equal to 0, and you get x equals 6 or x equals 2. And this is where students can make the mistake. If a student put 2 and 6 in their solution set, they would be wrong. Because something happened here. And you might not be aware of it unless I bring it to your attention. So here it is. When you square an equation on both sides to solve for a given variable, sometimes you create false positives. What do I mean by that? Does negative 3 equal 3? Does it? No, it doesn't. So this is false. But if I square both sides, something that was false becomes true. Why? Because squaring or raising both sides to an even power gets rid of negatives. So it makes opposites look the same. And that's what I mean by it sometimes creates false positives. So let me be even more clear about what's going on here. Originally, let's look all the way to the top. Originally, we had a square root function on the left. If that was y1, then that would start at 3/2. Oh, sorry, positive 3/2. My bad. So wrong side, right? Because you look at under the radical has to be bigger than or equal to 0, right? So this thing, the domain of this function, which is part of this equation, is 3/2 to infinity. So positive 3/2. So then it goes like this somehow, okay? And I'll draw it in a second. And then x minus 3 goes like this. Now, what this is suggesting is that this curve, the square root function, and this line meet in two places. It's saying it meets at 2 and at 6. Well, there's no way that they meet at 2. 1, 2 is right there, and this square root thing would be up here, but the line is down there, so they don't meet there. So we'll see why did that happen? Why did we get that solution 2? And then we have 1, 2, 3, 4, 5, 6. Could they meet here? Absolutely they could meet there. So the only solution that's valid here is the 6. What am I trying to say to you guys? When you square both sides, sometimes you create extraneous solutions. So when you get a solution, or you get two of them, you have to test your solutions in the original equation. If you plug in 2 here, you get 4. 4 minus 3 is 1. The square root of 1 is 1. And you'll notice that this equation is at a height of 1 when we are at 2. On this side, 2 minus 3 is negative 1. Negative 1 does not equal 1. These guys do not equal each other. 1 is at 1, 1 is at negative 1. But if you square 1 and you square negative 1, don't you get the same thing? Yeah. Squaring creates false positives. Let me make one further observation here. When you square both sides, you turn something that was radical, that was curved like this, and linear, that was straight like this, that only had one intersection in this case, into something that is straight and parabolic. So this thing, the left side, would now look like this after you squared it. Let me keep that going. This one is a squaring function shifted over 3. 1, 2, 3, right there. 1, 2, 1, 3, 4. So you would get a parabola like this. How many places does the parabola hit this line? 2. At 2 and at, you guessed it, 6. This has 2 solutions. Does this? Not necessarily. All right, so whenever you solve a radical equation, be sure to check your solutions. Sometimes they'll both work. It'll hit twice. Sometimes you'll just have one intersection. Check your solutions. All right. So 2 is not a solution. Let's go to this part here. We're looking at where I was calling this y1 and this y2. We're basically looking where y1 is below y2. And if you use intersection of graphs method, then this is your graph. We want where is y1 below y2. This is y1. This is y2. Well, here's your relevant feasible domain. This graph begins at 3/2. So on your number line, you have 3/2, you have 6, and you have infinity. And this will be true either in here or out there. It can't be true before 3/2 because x minus 3 can't be bigger than something that doesn't exist. And where does this graph begin? This graph begins at 3/2, right? So it's important when you're solving a radical equation to figure out what the domain, the feasible domain is, or the domain of possibility. In general, x could be from negative infinity to infinity normally, but because inside of this equation there is a square root function embedded in there, you got to look at the domain of this square root function. What restrictions does the presence of the square root impose upon solutions of x? Well, it tells us all the way down here, x must be bigger than or equal to 3/2. All right, where's y1 below? Where's the curve below the line? It looks like after 6 it is. So the answer here would be this way. And because it says below or equal to, I can include where they're equal. So that's how you would do it by graphing. If you did it by checking a point, you'd still have to know what the domain of possibility was. That it begins at 3/2, and that 6 is an important point because it is a solution to the equation. The boundary between greater than and less than is always equal to. So this is like a crossing point, always. You saw it's the intersection on here, but if you had done x-intercept method, it would be the 0 of the function. So how do we do this by test points? Pick a value. Pick 10, for example. 10 is in this region of the domain. You plug it in. Is 2 times 10 minus 3 less than 10 minus 3 is 17. Is the square root of 17 less than 7? Yes, because the square root of 16 is about 4, so this is a little bigger than 4, which is still going to be less than 7. So this would be a yes, and this would be a no if you tried that one. Okay, let's do the last one here. Here we're looking for where y1 is above y2. Where is the curve above the line? And we can use the graphs I've already drawn. Let me see. y1 is above y2 before 6. How long before 6? A lot of students make the mistake of saying, oh, before 6 works, so it's negative infinity to 6. But no, it's not. Because the domain of possibility ends at 3/2. You don't have to negative infinity here. So your answer is just between here and here. Now the question is, can I include 6 this time? I'm looking where y1 is greater than y2. At 3/2, y1 is above y2. At here, it's above, it's above, it's above, it's above. It's equal to. At 6, they're equal. I cannot include this. So my answer here would be 3/2 to 6 with a parenthesis. And actually, I failed to put the answer here. It was 6 to infinity. So that's how you do those. You could also do x-intercept method. I'll just make a comment on that. But if this works for you, you can stop the video. If you wanted to do x-intercept method in your calculator, you would have to move everything over to one side, and you would be looking for where that thing, for this problem, number 19, is below 0. Call this y1. Plug it in your calculator, see where it's below 0. When you plug this in your calculator, you will get a graph. And that graph, I will tell you, I think it would start at, when this is 3/2, this is 0. Negative 3/2 plus 3 would be at 1.5. So 3/2, it would be at 1.5. So it would start up here, and then the graph would be going down, and at 6 it would go through. But before 3/2, you would see nothing. From 3/2 to 6 it would be positive. Here we're looking for where it's below 0, so that's after 6, below or equal to 0, so it would be 6 to infinity. I'm sorry I don't have my graphing calculator on me, or I would actually show you how to do this. But there you go. And your answer for the other one would be the opposite, right? If you're looking where this is above, then you're going to move everything over. It's going to look just like this one, except this is going to be going the other way. So you're looking where y1 is above 0. This is what we're calling y1. It's above 0. Before 6. Where does it begin? At 3/2. So it's 3/2 to 6. All right. I'm going to do another one in a moment. Check it out. Bye.